Okay, so before we move on, good enough to summary those finds that we've had. Right, we learned right, this relation right here, you could also write this as sort of a better way to maybe understand it is shear force, linear proportional to radius. That's a pretty big one. We also derived the actual velocity profile. Which is nice. And things about this, well, some classic ones, the velocity as a whole will go up if the pressure gradient goes up, right? Or if the diameter goes up, or if the viscosity decreases. So if you have a less viscous fluid, it's going to flow faster through the pipe to a certain degree, because this won't be true. This will not be true if you get too less viscous and become air, because then it will go turbulent, and then we won't have that shear relationship that we made here to get here. But for the range we're considering, it's the case. One more thing, we know that the maximum velocity, right, is just this thing, right? So that's interesting. Someone could tell you that if you can't have, I'm gonna go faster than that, you can calculate it. We also figured out there's a V bar. It's just half this value. So if you want this V bar, you gotta calculate this thing first based on properties. And this relates to if I wanna just multiply two numbers together, no integration, right? If I just wanna multiply two numbers together to get volumetric flow rate, I have to use the V bar, and it comes from here. So this is just convenient. It's just convenient to calculate flow. And then we also can calculate the flow rate a different way, given properties. Right? And the takeaway here was that's very sensitive to the diameter of the pipe. So overview, that's why you do analysis. That's why you take careful steps of math, is to get these quantities. And now we're going to start using the quantities. But before we do that, we will have to non-dimensionalize our expressions. I'll just go on here. So we have the non-dimensional forms is what we want. Right? And that's true because non-dimensional expressions have the benefit that, right, that they're true regardless of the scale. Right? So this is D, right? This is little d, right? And then you could have a, right, big flow rate, little flow rate. But if I can write all the things I've done in non-dimensional form, they're going to be true for a much, much larger class of problems. So that's just a motive, right? That's just kind of trying to express to you why anyone would want to do this non-dimensionalization stuff. And that's mainly because you want your things to be true no matter what. So I'll let this file stop. Next time we'll do it.